Thank you very much for inviting me to speak here. So I'm going to talk about joint work with Petrov, Alexander Petrov. And well, this, I'm going to explain this what non-commutative crystalline cohomology is. We'll give a very simple algebraic construction. So, but I have to warn you that there are many other constructions, probably of the same objects. Sometimes it's known that you get the same objects, sometimes it's not. One of them is due to Kalesin, and it's not known that this cohomology theory coincides with ours. On the other hand, there is something about topological cyclic homology, and there it is known that we get essentially the same object. So, okay, so what is, first I want to tell you what, a little bit, just to set the context, how I want to think about crystalline homology. So for this purpose I will fix some field K, north field. And I will assume that its characteristic of K is some prime number P greater than 2. So the story is slightly different when P is 2. And VWM is meant for vectors. For example, we can take A equal to E, and then WM equal to Z. And then, so the crystalline cohomology is a functor, an invariant functor from the category of smooth schemes over my field K to the derived category of modules over the weak vectors. So I can take a homology of this complex, and then I get what's called crystalline homology groups. These are modules here over the weak vectors, and there are this functor satisfies two properties that I want to mention. So first of all, if I consider this complex and tensor it over weak vectors with K, then I get just the derived conclusion. So this is just the eigenhomology of the complex of differential forms. The reason why I want to look at think of this as a functor of the derived category rather than functor to graded groups is to have a nice formulation of this property. Otherwise, there was some coefficient form. If this is if cohomology is not there.
Is M fixed, or is it all M? Or is
yeah, so M is fixed. Yes.
But do we allow M equals infinity?
Do we allow M equal infinity?
So
I prefer first work with defining them, and then if I need, I can go. So there is a. I can. Oh, I will mention it afterwards. Okay.
So it's like L-adic cohomology.
So. Okay. So this is first property, and the second property is that if I have a smooth lifting of my scheme, so if I have X tilde, which is a smooth scheme over W M K, such that X tilde, so this is a lifting, then, so X, then R gamma raise of X tilde is just the Dirac cohomology of the lift.
Relative to the
Relative to the difference. Right. So these are the two properties, and so right. So if so, this factor depends on n, and so maybe I will mention it here. So so if I put n here in my entry to assign the dependence on m, then it also has a property that when I say tensor it is w n minus 1 over k of k over w n, then I get the previous r gamma is n minus 1. That means that these functors form an inverse system. You can take the limit, and so then you get crystalline cohomology, which takes values in just in derived category of WK modulus. M is infinity.
So those two properties, 1 and 2, determine uniquely the functor?
No, I don't know this. That's a good question, but I don't know.
Is there some compatibility with the Frobenius?
With the Frobenius, well, Frobenius that's by materiality, it's a functor. What do you mean compatibility with the Frobenius?
Something that I don't know.
Mm-hmm.
So
we're perfectly allowed to have a scheme over Wm of k that does not lift to Wm plus 1.
yes, yes. So, well, one corollary of this, of the existence of this functor, satisfying this property, is that well, this right hand side of this identity does not depend on the lift. So that means that if I have, if I give myself the scheme over k and two liftings, then this Dirac cohomology groups coincide, and well, moreover, if I have any corollary, if I have x smooth scheme over Wm, and some endomorphism, some map V tilde, which is equal to identity modulo V, then its section on the Dirac cohomology.
What means that?
Yeah, it means that it's restriction, right? It means that its distinction to x is so x is okay. Yeah, it's tensor with k's identity. That's what it means. Then the action of phi tilde on r down there is equal to, no, I did it. Right? Just because you have functorial isomorphism and endomorphisms of, so here you have action of endomorphism of x, and here those endomorphisms act via restriction to x. So in particular, if I have an endomorphism which is equal to identity modulo p, it means that here that's trivial, so we'll get this product. And in fact, once it turns out that the very existence of this function follows from this corollary. That's what I want to explain. First, I am going to recall you how you prove this corollary. And the proof is essentially a Cartan homotopic formula. And then I will say a few words how you can use having this corollary construct the function. Okay? So, so let me recall the Cartan's formula. So it's the following. So I have a smooth scheme over some basis, and then I have a vector field theta, which is vector field. See this, and then I have differential force, relative differential force, and I have the operator iota, which is substitution of the vector field. So it goes to omega dot minus 1. And it has the property that the commutator of this iota and Dirac differential is equal to the E derivative with respect. And the commutator is, of course, means here the Subia braided commutator, so it's iota composed with iota d plus d minus iota. So this iota has two additional properties which can play important role. So first of all, it has the property that the commutator of the E derivative and this iota prime. This is another vector field. Is equal to iota commutator vector prime. And also another property is that this iota theta and iota theta prime commute. Again, everything is all commutators here are great. So now let's prove this.
Could you explain that for me? Is that the definition of L theta?
This is substitution of a vector field into a differential form.
Is it the definition of L theta?
L theta, no, it's Lie derivative. It's Lie derivative. So I want to think, I want to think of Lie derivative for me is something more fundamental. It's if I have a vector field, it acts on functions by derivations,
of course.
And then it acts on the Dirac complex. It's characterized by the property that it satisfies the Leibniz formula with respect to multiplication and commutes with Dirac differentials.
So who is I theta?
I theta now. So I have action of the Lie derivative here, and And now I define iota theta to be the substitution of a vector field in the differential form.
Yeah, okay.
And then I have this. So in particular, it implies that the action of so this is used to prove that action of this Lie derivative on the Rank cohomology is trivial, and indeed it's so in fact this action on the of Lie derivative on the Durand complex is homotopy equivalent to 0 and iota is common. So, but I can do more. I can look at the so if I have so proof of corollary. So if I have my f tilde, I can look at I can do the following. So I have f tilde, and it acts on functions. So and f tilde star is identity mod p. So if I have just a module over W and the morphism with this property, I can take its logarithm. Its logarithm is well defined. And I will define theta. Theta is going to be derivation just to be the logarithm.
Do you assume P is greater than 2?
What?
Do you assume that P
Yes, P is greater than 2. I think it's P. What?
But I think you can prove it without. Yeah, you can prove it without taking the logarithm, so that it works for all P. So it's just
it works for P,
it's a
but
bit artificial.
what?
It's a bit artificial.
It's a bit artificial, and there are some. I don't think that you can make this homotopy compatible with the restriction map, so that it doesn't quite work this same way when P is 2. So I don't want this. So I will take the logarithm, which is just given by standard formula. It's negative sum 1 minus P star I. So it makes sense because of this assumption, and this is a global derivation. The global. I think of this as a vector field on x tilde, t x tilde W. Okay. So now with help of this vector field, I can rewrite the action of P star, P tilde star on the Durand complex. This text here. And this is equal to exponential. So I will write it as sum of L theta and over n. Again, it makes sense because of this, because this theta is equal to 0 modulo p. Since since my phi is equal to identity modulo p, this is equal to 0 modulo p, and my assumption that p is greater than 2 implies that this is equal to 0. No? And therefore, I can take the exponential. And I claim that so the action of the Durand complex is just given by this formula. What I claim is the Lie derivative. Now, okay, so I have this expression. I want to show that the action of this iterator on the Durand complex is homotopy equivalent to the identity. And indeed, so the zero term, when n is 0, it's just identity. And when n is greater than 0, well, I have L theta here. So which is homotopy equivalent to the identity. So I can write down an explicit formula for the homotopy. So if I define H P to be sum of your vector n minus 1 over n factorial, then it has a property that indeed the commutative of the run differential in this H is equal to integral, which proves that this this operator acts trivially on the derivatives. And moreover, I have a very explicit homotopy. So this homotopy is canonical, so it has in fact this argument proves a stronger state. Not only that the action of an endomorphism of X, automorphism of X, which is equal to identity modulo T, is trivial, but also, in fact, it proves that the action of the entire group of automorphisms, which are equal to identity modulo P, is homotopically trivial. And I explain precisely what it means. It means that these homotopies that I constructed here are coherent when you verify T. In this case, it just means that it satisfies quasi-cycle condition. Oh, sorry. So, you can suppose you have some discrete group acting on a cortex, and you can ask what it means that the action is homotopically trivial. So, one way to say it would be the following. So, if G is your group, then you can form a simplicial group. So you think of this as a contractible group, and to say that action of G is trivial, but for me it means that the action of G extends to a simplicial action of this guy. And this formula precisely means this, right? So, okay, so now I have, I prove the corollary, and I prove the stronger, even the stronger statement. If I could use a bit of formal geometry just to say that, okay, so that's to derive from this fact, formally, the existence of our God. So one way to do it would be the following. So, so I don't explain how, I do not give you details, but explain the idea. So you take your X, and I want to construct crystalline cohomology. So I cover my X with affine open sets. And every affine variety over K admits a lifting over a smooth affine variety admits a lifting over Wn K. So this, moreover, any two such liftings are isomorphic, though the isomorphism is not canonical. So you have isomorphismal liftings here we have isomorphism of liftings here and also here. So, though because the isomorphism is not canonical, you cannot make those isomorphism on the intersection to satisfy the recital condition in G. So then what you can do, so if once you have fixed such a lifting, you can write the de Rham complex. You can try to write something as you can consider some OI of UI theta. This is the de Rham complex of UI. Here I can consider UI in the second piece of G. Well, I want to write down something as the de Rham Czech complex, where the cones are going to be the de Rham complexes of this of UI, which are schemes over W and P. Columns and rows are going to be central Czech complexes. So there is though a little problem here. So by choosing isomorphism between the liftings of pairwise intersection, I can define these horizontal maps that the rows in general are not going to be complexes. The differential is not going to be zero. This is because my liftings, though they are isomorphic on pairwise intersection, they do not satisfy cocycle condition. So the square will not be in general zero. However, the square is expressed in terms of the difference between two isomorphisms between the liftings on this triple intersection. And so I have this sort of Czech map, the restriction maps, and they have the de Rham differential. And if I take the sum of all and try to form the total complex, the differential is not going to be zero, but I can correct it using this homologies here to make the differential equal to zero. And the reason why it's possible is precisely this condition. Okay? So now I want to do something like this in non-commutative setting. To recall the setup, we'll start with recall that if I have an algebra E over some commutative algebra, smooth commutative algebra over R, smooth commutative, then differential forms on E relative to R can be interpreted as 4 over E times of E. Well, I will write opposite, though because A is commutative, it doesn't really matter. But the key point I want to make is that whereas the left-hand side makes sense only for commutative algebras, the right-hand side is defined for all algebras. So, moreover, so the discovery of Zigan and Kohn is that even the de Rham differential has a makes sense for any algebra. So if I start with any associative, usually the right, right. makes sense for any object. So, the construction of this differential, which is
So in this left blackboard, what's the enhancement of differential?
say it again.
In the left blackboard,
This is the round differential.
yes, but over there where you don't get the square vanishing condition, you're enhancing somehow your differential with these.
Oh,
edges.
you're
Yeah,
talking about
but-
this
yeah. What's D? What's the definition of D?
or D.
The one that works, I mean, the one that gives you the.
Okay. So what you do, so once you choose, once you have liftings and you choose isomorphism between the two liftings on pairwise intersection, you get naturally all these maps.
Mhm.
So then what is the definition of D? So you take the round differential plus this map and plus this harmonic, which for all triple intersections.
Mhm.
So you correct it by that. Okay. So the construction of this map, which is called D. Again, so the point that I want to make is that this turns out that this part is defined for any associative object. And I don't think that I should make sense me to write down definition of this. What I rather want to, so because it's kind of non-trivial. So tors have you can compute it in many ways using arbitrary flag or projective or free resolution of ASAB module. The definition of P essentially uses a very explicit the bar resolution for this C. So you take your algebra A, and then these tors, which are also called the cohomology of V, can be computed using a specific canonical free resolution for A in the category of bimodules. So the resultant complex is the following form. So again, it computes these tors. So the differential here is for example, this differential is A1, A0, A1 to A0, A1 minus A1, A0, and here you write these elements A0, A1 from the circle, and the differential is obtained as follows. You take so for each interval in this circle, you take the product of the corresponding entries, A0, A1, for example, and A0, A1, and A2 goes to A0, A1, A2 minus A0, A1, A2. Plus this is A2, A0, A. Okay, so this is what's called the Gaussian differential, and it computes these tors for any associative object. So in order to define this analog of the drum differential, one constructed a map on the chain level. It goes in this direction. So I will have D delta option, and this will be my, this is one map, Z, and it has two properties. That first of all, B squared is 0, And secondly, it can use with Cauchy differential. So once you have these properties, well, in particular, it defines this V defines a map from F homology of this complex to N plus first, so it defines me this map. And then, I could define the rank homology of an associative algebra just to be, well, since B squared is 0, I could consider so this complexes with differential B, but there is a much better way to, it's better to, instead of first taking homology with respect to Cauchy differential, take components. So you can introduce a variable u of degree 2 and consider consider this complex CA tensor is well, consider a Laurent series and introduce differential delta Cauchy plus B u here. So since B has homological degree -1, U has degree 2, so this has degree 1, and these two properties imply that this is a complex. And this is the periodic cyclic complex, which I will denote as Cp of. So that's this is the non-commutative. For me, it's going to be the non-commutative kind of substitute for the Durand complex here. And indeed, when A is smooth commutative algebra over a field of characteristic 0, then homology of this complex, first of all, it's clear that it's 2 periodic, and its homology in odd degrees is going to be the sum of Durand homology in even degrees, and in odd degrees it's going to be odd part of the Durand homology groups. So it's indeed related to this. So, so let me call this sum delta, and in order to, so I want to generalize this definition a little bit.
What is U again?
U is just a formal variable.
What did you do?
It has a topological meaning.
It has a topological meaning. This is related to the circle action, but so so how I want to need to talk about. I need to do generalization. So first of all, well. So I didn't tell you what A. I said that A is an algebra. An algebra over what? So in the very definition of this complex, there is this tensor product, and therefore it's important over which commutative algebra you take the tensor product, right? You can take the tensor product over Z, over some field, over something. So I can start with any algebra, pick some base ring.
I'm sorry, what was the advantage of defining the CPA?
Say it again?
The advantage of CPA, what was it?
So first of all, CPA is defined for any associative algebra, and in the case when my algebra is smooth commutative,
It's the same.
it's related to the Durand homology.
Cohomologies of even.
That's it. So I will assume that A is any associative flat over R. So for any associative algebra flat over R, I can define this complex by putting R here, and I know this is my cohomology. I will write the base here, so this is CP over. So one advantage of this additional generality is that now by the functoriality of this construction, any derivation set of my algebra A, it's on this complex. So, well, how to see this? So if a derivation of an algebra is the same thing as an automorphism of algebra A of epsilon over R of x. So I introduce a new variable whose square, which commutes with R, whose square is 0. So a derivation is like vector field. So a vector field is a tangent vector to the group of automorphism of the algebra, right? So that means that 1 plus theta defines an automorphism of this algebra, which is equal to 0, which is equal to the identity modulo epsilon. So this
R linear?
what?
R
R linear, yes.
R linear derivative.
Yes,
Okay.
yes.
That's fine.
So in particular, theta defines an action of so 1 plus theta is x on by functoriality on Cp A epsilon over R epsilon, and I define the Lie derivative as follows. This is identity plus epsilon times Lie derivative. So here are so this formula should be understood as follows. So clearly this periodic cyclic complex is obtained from this complex just by tensoring with R of epsilon. So this expression really makes sense. So by the very functoriality of this construction and compatibility with the base change, you get the action of this theory.
Sorry, can you remind me how do you define L theta?
L theta?
Yeah.
So here is the definition. So by functoriality, I have action, so this 1 plus theta, so if theta is the derivation of it, then 1 plus theta is an automorphism of it. Therefore, it acts on the periodic cyclic homology of this algebra. But the periodic cyclic homology of this algebra is nothing else but Cp of A over R. Tensor with K of epsilon, with R of epsilon. Over R. So, and this automorphism of this module is clearly equal to the identity modulo epsilon. Therefore, I can write it as identity plus epsilon times something, and this something is the Lie derivative. Does it make sense?
Yes, but is it true that the periodic cyclic complex behaves well with respect to phase that base changes?
Yes, yes, and it's essentially by definition. Okay, so so the next input is the analog of the substitution. So
For the best change, you need to use completed tensor products. Because
yeah, but I don't think that appears here.
well, here is yeah, but I am writing it here.
So okay, so this so you can since we have now the action of derivations, Lie derivatives. So the next step in building non-commutative calculus would be to find an analog of the Cartan's homotopy form. And indeed it was done by Kessler, so he constructed, for any derivation, he constructed a map iota theta, which has the property that it's commutative with delta is equal to the Lie derivative. It also has the property that for two derivations, f theta, iota theta prime is equal to iota theta prime. What is not true in general, however, is that this operator is commute. And this is the source of many problems, and in particular the problem, this problem appears in what I'm trying to do. So it's not equal to 0 anymore. Okay, so so in particular, any Lie derivative, any derivation acts by the action of Lie derivative, the action of derivation by Lie derivative on this complex is homotopy equivalent to 0. Using this non-commutative Cartan's form. So, so now what is my goal? I want to start with an algebra over finite over some field of characteristic 0, and I want to construct, I will write here, so so I will have a functor which is C decrease from algebras over field K, the characteristic of K is equal to K, and it's greater than Q, and it's perfect. And so this will be the derived category of WM modules. And it has two properties. That first property is that if I take CD with and tensor it with K over W, then I get what we do. And the second property is that if A is tilde is a lifting, flat lifting. So it's flat. And A tilde is then I want to have this is just CPU. Okay. So that should be a quasi-asymptotic. So okay, I think I have 10 minutes. In order to do this, first I need to generalize, well, kind of ask a more general question, right? Really, if I want to do it just for associative algebras, even if I want to do it interested only in associative algebras, the construction goes through differential gradient functions. So I need dg. How I want to think of periodic cyclic homology of a DG algebra. So what is a DG algebra? It's a usual algebra, graded algebra, together with a differential, right? So this is D. So I have first of all, differential graded algebra. Again, it's a graded algebra plus I have differential. Plus we have a derivation of this graded algebra, and its degree is of d is equal to 1, and its square is equal to 0. Since I'm working over a field of characteristic different from 2, it's equivalent to saying that its commutator is itself, it's just 2d squared, right, is equal to 0. Why I want to write it in this formula? Well, the commutator of derivations is again a derivation, so for me it makes more sense to take the okay, so if I want to define the periodic cyclic complex of this, well, the way I want to think about this is the following. So at first I forget about the differential, and I look at the graded algebra. So, and it has, as a graded algebra, it has this differential. The only thing that I want to now remember is how, well, the way I define the total gradient of this complex. Remember that this complex is formed by tensor powers of A. So now my algebra is graded, so I want to take the total gradient, right? So I will have sum, so my gradient here is going to be the total gradient, and the differential is given by the formula over there. So this is just the function, the periodic cyclic complex of a graded algebra. Now I want to remember this derivation here and incorporate it into this definition. And the way I want to do it is just to reiterate with respect to this. Okay? So, okay, so this is by definition, this is periodic cyclic homology of a differential gradient. Okay. So, and again, everywhere is to remember the basic. Now, we try to use, so in order to construct this CP, we try to use this Cartan homotopy form. And so the idea was very simple. So if you start with any differential gradient algebra, you can replace it by a quasi-isomorphic algebra, which is semi-free. A semi-free algebra, in particular this graded algebra, is free algebra. It's just a tensor algebra. But you have a non-complicated differential. Any semi-free algebra, well, any tensor algebra, of course, admits a lifting, a unique lifting over grid vectors. Moreover, you can even lift this derivation to a derivation of the lifted algebra. tilde squared is not going to be zero algebra. You can't achieve this. So d tilde squared is going to be, so it's, it's 1/2. So it's a derivation, but in general it's not equal to 0. So, well, you can start with an algebra over a field K. You can take its leave the graded algebra over bit vectors, leave this d tilde to a derivation, and write the formula, similar formula, where you have Cp in tilde delta plus L d tilde. But the problem is that the square of this operator is not going to be zero even. This is precisely the abstraction. So, it turns out that you can correct it by adding iota d tilde squared. Then you have more terms. So, the reason why you can correct it is exactly the same as in the case of the Durand complex and the crystalline cohomology. But unfortunately, so though this construction, well, you can make it work when n is 2 and with some efforts when n is 3, the lack of this commutativity is really a problem. So it's very difficult to write down all these homotopes in general. So the action of automorphisms, which are equal to identity modulo P, is not homotopically, well, at least I don't know why it's homotopically. It's very difficult to realize. So
this failure of commutativity, I mean, it is kind of E2 commutative?
It's E2 commutative, but, well, apparently one can write all these homotopes.
Yeah, but probably you need just to use this formulity of second Lamarckian calculus.
Yeah, but it's over a field of characteristics. It doesn't even make sense over a field of characteristics. So, and now I will tell you the answer. So the construction. The construction is very simple, and it's it doesn't make sense in at least kind of in classical algebraic geometry. So what you do is the following: you take C. So you take your algebra E. So A is over here field of characteristics 0, right? So it's maybe differential graded algebra. Over here field of characteristics. But of course, an algebra over a field of characteristic P is in particular, it's an algebra over W. It's not flat. But I can still look at its periodic cyclic homology just by replacing this algebra by a flat algebra. So, for example, if I have, it's not the end of the definition, but it's almost there. So, for example, if I have just algebra K, how one can compute its, so suppose I want to compute its periodic cyclic homology, or maybe let's make this thing simpler. So let's suppose I have algebra Fp, and I want to compute its periodic cyclic homology over Z. So what I'm supposed to do, I have to write down a quasi-isomorphic algebra, which is flat over Z. And this algebra is just going to be Z, multiplication by, that's an algebra. It's a thing of, it's a miracle that it's an algebra. But it's true. So this is what I mean here, right? So the definition of this right-hand side is the following: you take A, you replace it by a quasi-isomorphic algebra, which is flat over this. And then what you do, you tensor it. So this is a module over Cp of K over Wm. So just because K is an algebra over K, this periodic cyclic homology satisfies certain, it's a monoidal functor in the sense that it's a module over. And so this is an algebra, and it admits a map to W and K. Well, for example, if you take the periodic cyclic homology of this algebra, it admits, so this is an algebra, its cohomology isn't characteristic P, right? Sorry, it's quasi-isomorphic to FP, but nevertheless, if you take its periodic cyclic homology, Cp of this algebra over Z, then you can check that this is the same as periodic cyclic homology of Z P goes to ZP, where this map is 0, right? And the reason for this is very simple. So first of all, it's easy that you can put P here everywhere. But now think, these two algebras are lifting of the same algebra, modulo P. So if you believe in the existence of the crystalline homology, these two groups must be the same. And this algebra, this is 0, admits a map to ZP, so you can you get a map from this guy to ZP. And the same argument can be used to construct a map of algebras from here to here. And this is the construction.
And you can remove M, so just consider everything of the vectors and will.
Yeah, yes.
No, but it's not in general the same as the limit.
Yeah, so you have to be careful. It's like crystalline homology, it's better. Okay.
You said at the beginning something about THH?
Yes, this is the same as TP. Namely, you take CHH, you take OK, and you take CPN. Well, it's in the case when K is so it's really a so yeah. So when you take fast to the limit, this thing goes to infinity. This CPN gets replaced by itself.
Yeah, but T you did take homology.
But in the end, so you have the story about the derivative and the Cartan formula and so on. But
So
but
it's
in the end, you give some construction independent.
yeah, but it's used this lead derivative and Cartan's formula is used first of all to construct this map, which probably can be done explicitly, but also it's used to prove that this guy has the two properties that I mentioned. So, namely, the most important is that if I have leads enough, then this guy coincides with the periodic cyclic homology of it. And this is where you need the Cartan's formula. So, and perhaps in this story, this periodic cyclic homology, with this topological homology, it was not known that this coincides with periodic cyclic homology of leads. So this is kind of a new, if you wish, it's new property. But on the other hand, you have some structure here which cannot be constructed, which I don't know how to see directly. For example, lift action of the Frobenius. So on the topological periodic cyclic homology, you have an action of the Frobenius, which therefore you have here, but it's very difficult to construct directly. Because in contrast with commutative case, when the Frobenius acts by contrariety, here you don't have action instantaneous.
Okay, more questions? Comments? Okay, let's take Stefan.